Next speaker will be Miles Lopes from University of California, Berkeley, right down the road from me. He's studying machine learning. He'll be speaking to us today about estimating unknown sparsity in compressed sensing. He has done his practicum at Sandia National Labs in California. So Miles, take it away.
Can you hear me all right? All right, so thank you for the introduction. So I work in the field of high-dimensional statistics, and compressed sensing is a topic that fits within that area. So this particular project was published, an early version of it was at ICML, the machine learning conference last year, and I'll be discussing some extensions I've been working on. So to give you an overview of compressed sensing, you can think of it as an alternative to the conventional analog to digital conversion pipeline. So one reason why you might be interested in seeking alternative is that this pipeline is very wasteful in compressing analog data into the digital format. So, regardless of the particular type of media, what you'd like to do instead is just directly measure the part of the signal that you're interested in, rather than acquiring way too much and then throwing the rest away. So said differently, what compressed sensing tries to do is it tries to merge acquisition and compression into just a single step. All right, so to make this more concrete, I have a 1 megapixel image. You can think of this as sort of being a raw image. And on the right, I have an approximation based on the top 25,000 wavelet coefficients. So as you can see, the images are nearly indistinguishable. So it would be of interest to design a camera such that you can acquire directly 25,000 pixels of information rather than acquire 1 million pixels of information. One way people have gone about trying to do this is to build what's called a single pixel camera. And this is research that's been ongoing at Rice University. The way it works is that an image or signal comes through a lens and it's projected off of what's called a DMD array. It stands for digital micromirror device. It's a grid of microscopic mirrors that can be programmed into different orientations to point either toward or away from the light source. And the reflected light is collected into a photodiode, and then that's passed to an AD converter, and the output is just a number. So mathematically, the way this is modeled is the input seen is simply a Euclidean vector in p-dimensional space, and the grid of mirrors is another vector in p-dimensional space, and the output of the diode can be interpreted as a noisy dot product of those two vectors. So obviously, we can't reconstruct an image from just a single number, so we have to take multiple single pixel shots in order to acquire the full image. The goal is that we can take only 25,000 single pixel shots and hope to get a good approximation rather than acquiring 1 million, as in the previous example. Okay, so compressed sensing is not limited to simply photography. It can be studied just abstractly as a linear inverse problem, and that's how I'll try and present it. So if we represent the ith measurement vector AI as a row of a matrix, then the whole collection of measurements can be written down as a linear equation plus noise. And the goal, just abstractly, is to design a matrix A and to take the measurements Y and then accurately recover X, or recover X as accurately as possible. All right, so the obstacle is that the dimension of X is very large, and the number of measurements we want to take is relatively small. So naively, this seems like an ill-posed inverse problem. And what saves us is that at least we hope, that the signal is sparse in some basis. And that takes what is an ill-posed problem and turns it into a well-posed one or a nearly well-posed one. Just a couple technical points. So A is definitely a singular matrix. And then in case you're wondering about the particular basis in which I represent the signal, that can kind of be glossed over abstractly by precomposing the matrix with a relevant orthogonal matrix. So that's just a detail to kind of mention. OK, so that's the setup. How do we go about recovering X from these measurements? And this process can be kind of viewed as the fundamental theorem of compressed sensing, as sort of the starting point for this topic back in 2006 or so. So suppose we have a linear model, and the noise vector is bounded by some constant epsilon naught. And we define our approximation to be the solution to this convex optimization problem. So minimize the L1 norm subject to a goodness of fit constraint. And you'll notice that the true signal is a feasible point. So there is at least one solution. And define the sparsity of x, or the L0 norm, as simply the number of non-zero coordinates. Okay. Now, in this notation, the very interesting and deep fact is that if you draw the matrix A randomly from a suitable ensemble, and if the number of measurements is at least on the same order as the sparsity level times a log factor, then with very high probability, the recovered, the solution to that optimization problem will be indeed close to the true signal. Okay, so this fact was published in these papers referenced here. All right, so this is sort of a coarse summary of compressed sensing. So now I'll try and get to my contribution. As you'll notice, the sparsity plays an important role in formulating this result. It tells us how many measurements we need to take in order to hope to get an accurate solution. The trouble is that in most works on compressed sensing, especially theoretical ones, the sparsity level is treated as a known parameter, even though the signal is unknown. So that leaves a number of very basic questions. So in practice, how can we check if a signal is actually sparse in the basis that we've chosen to work in? So in other words, how can we check whether or not the compressed sensing framework is even sort of a valid strategy? Second question is, how do we know if we've even taken enough measurements? Alternatively, if we knew the L0 norm, that would allow us to take just enough measurements and make the process as efficient as possible. So these were the kinds of questions that motivated me to try and estimate this single number, the L0 norm, as a estimation problem. All right, so there's one other issue, which is that the L0 norm is a very idealized measure of sparsity, meaning that in practice, we rarely have signals that have coordinates that are identically equal to 0. Most of the time, there's a little bit of noise or whatever. So if you take the L0 norm of a signal whose coordinates are all non-zero, you'll get a very uninteresting answer. And so even if x has a few very large coordinates, the rest are small yet non-zero, this L0 norm doesn't give you a very descriptive answer. So what can we do to try and find a surrogate? So I propose to derive one along the following lines. So for any non-zero signal, we can define a probability distribution on the index set 1 through p. So just define the probability mass to be proportional to the magnitude of the jth index and normalize it. So if you drew a random index, capital J, from that distribution, it's sort of clear that J is most likely to fall in the indices where the coordinate xj is large. So said differently, the effective number of states of this random variable is that number of states should be equal to the effective, or the number of large coordinates of x. So the usefulness of this sort of conceptual equation is that we can estimate or measure the left-hand side using entropy. So the effective number of states of a distribution can be measured in terms of entropy just by taking its exponential. It's sort of a basic fact from information theory. But rather than using the Shannon entropy, I want to use something slightly more general, which turns out to be convenient for reasons I can't explain at the moment. But so if we plug the distribution I defined a moment ago into what's called the Rainey entropy, and you take its exponential, proceeding along these lines, in essence, defines the number of effective coordinates of vector x, which I defined to be SQ of x. So it turns out that this number can be expressed as a ratio of LQ norms, and that is very convenient for reasons I'll explain later. Okay, so this is the quantity that I'd like to estimate. And to convince you that it's not just some random number, it actually has meaning, I've plotted 3 different vectors in R100, and I've plotted their corresponding S2 of x values on the x-axis. So for the red signal, you can see that it has roughly 16 effective coordinates, and the rest are relatively small. So that, in fact, matches up with what we get. Similarly, for the black and blue signals, the S2 of x value corresponds roughly to where the elbow is in the decay plot. running a little bit slow on time, so I'll try and get to the end. So how do we go about estimating this parameter? So it's defined as a ratio of LQ norms, so all we need to do is estimate an LQ norm for general Q. And that's what I propose to do. So the case Q equal 2 is the simplest, and then I'll try and explain how general Q is generalized off of that. If we draw the measurement vector AI to have IID coordinates from a standard normal distribution, it's kind of a basic fact that if you dot that Gaussian vector into X, that dot product is itself a Gaussian variable, and its variance is given by the 2 norms squared of X. So what that means is that if there was no noise, if we had perfectly noiseless measurements, Y1 through Yn would be a sample from a normal distribution whose variance is the parameter that we'd like to estimate. So the sample variance would do perfectly well. We'd get a 1 over square root n convergence rate, and things would be easy. Now, deconvolving introduces a lot of complexity that I won't really have time to discuss, but this gives you the right idea for the case of Q equals 2. Another insight that you can gain from this simple example is that we've essentially converted the problem of estimating sparsity into a univariate or a one-dimensional estimation problem. So estimating the norm doesn't depend on the dimension of X or on the sparsity of X. It only depends on X through its norm. All right, so now the question is, how do we generalize to more general Q? So in terms of general, I can do any Q between 0 and 2. And the way this works is, instead of drawing the vector AI to have IID Gaussian coordinates, we draw the coordinates from what's called a stable distribution. And so the Gaussian is probably the most well-known stable law. So the principle is very much the same as before. If you dot a vector whose coordinates are IID stable into X, that dot product is itself a stable random variable. And now the trick is that the scale parameter of this stable distribution is the LQ norm of X rather than the L2 norm of X. Now, estimating scale parameters for general stable laws is a more complex problem, and then when you throw in deconvolution to boot, it's even more complex. So that's really the technical challenge that was a contribution to my work. This is essentially the idea underlying my estimation method. To summarize the contributions of this project, I've derived an alternative measure of sparsity to the L0 norm. I've showed that well, I didn't present it to you, but I managed to show that SQ of X is a meaningful measure of sample complexity for recovering X. I derived an estimator for SQ of X that doesn't rely on any sparsity assumptions or on the dimension of X. I proved a central limit theorem for the estimator and obtained exact formulas for its limiting variance. So that enables you to get confidence intervals and perform hypothesis tests related to sparsity. And also, I validated the asymptotic calculations with simulation. So finally, I'd like to thank my thesis advisor, Peter Bickel at UC Berkeley, my practicum advisor at Sandia Livermore, Philip Kegelmeyer, the CSGF Fellowship, and everyone at the Krell Institute for making the fellowship possible. So thank you very much.